Alright guys, good morning. Today we're going to carry on our discussion about dichotomy and VC dimension. So in the previous lecture we talked about how we're going to exchange, how we're going to find a better substitute for our union bound, which was using M as the number of unions of the hypothesis in our hypothesis H. So say we had H1 up to Hm, and we assume that these are disjoint events. So in order to generalize the Hofstadter's inequality, we had to make a union of the probabilities of all of these m's. And in variety of cases, such as perceptron, which was one of the simpler cases, we saw that in many cases, for instance, suppose this is a 2D case, so many of these hypotheses are overlapping in a way. So this is like H1, this is H2, this is H3. So many of these hypotheses are overlapping to the point that if we make a union bound over the M, it's as if we are counting them 3 times. And this will give us a much higher ceiling for our complexity of the model, and it's not as accurate as needed. So we thought, how are we going to exchange, how are we going to find a better upper bound to use instead of M? And then we came along dichotomy set. So I'm just going to recap what the dichotomy was. So we assumed our set of hypotheses is again called capital H, and we have data points from 1 to n, right? So we define a dichotomy vector such as this, given our data points, and we mentioned that suppose you have several points here, like in this case we have 3 points, x1, x2, and x3, right? And each of these cases are accepting 2 values, right? +1 or -1. So we assume that if we put the opaque cover, so we don't see the rest of the space, which is the capital X, and we put holes on that specific paper and put it on top of this plane, right? So that we only see through the holes these 3 data points, right? And we thought, what are the maximum different combination of hypotheses that we can use in order to successfully classify these 2 values, given that either of these are plus or 1. So this can accept plus or 1, this can accept plus or 1, this can accept also plus and 1, right? So one way would be I put my hypothesis here, right? This is my H1. In this case, I make x2, suppose that was -1, and these 2 becomes +1, right? On the other case, if I assume this was plus, the other 2 would be minus, right? So these are 2 cases. What if I put my hypothesis here, right? On the both case, so this was x2 actually. x2, x1, x3, right? So x1 becomes -1, and 2 and 3 are pluses, or the other way around. And we carried on expanding the dichotomy set. So dichotomy by name is like duality. So because we have a binary classification, each of the values can accept 2 classes, right? And we expand this to the point that we understood upper bound of the number of dichotomies for the perceptron could be smaller than or equal to 2 to the raise of n. We have n values, each of them accepts binary levels. Thus, the upper bound could be 2 to the raise of n. And through some examples, we noticed that using 2 to the raise of n is much better than m, because m in many cases was infinite value, right? As an example, you had pluses here, you had minuses there, right? In the case of perceptron, you have infinite number of hypotheses that you can use in order to successfully classify these two classes, right? So we saw that even for a simple example of perceptron, in many cases m becomes infinite. So it doesn't give us a good upper bound for the complexity of the model that we want to have. That's why we thought about dichotomy set, and then we understood that given the number of points, in this case was 3, in many cases we see that it's smaller than equal to 2 minus n. There are several cases that we discussed last session that because of the nonlinearity, it doesn't shatter up to 2 to the raise of n, and it's lower, and that's why we defined these shatters here. So we say if the number of hypotheses given the points, so h of x1, in this case h of x1, x2, x3 is 2 to the raise of n, we say it shatters the data points. In the case of four data points, when they were here, like this, theoretically this could have been 16, but we saw that because it becomes a nonlinearity in these two cases, if there are 2 pluses and 2 minuses, there's no way, if this is minus and this is plus, right? Minus, plus, yeah, there's no way you can distinguish this with one perceptron or the other way around. That's why we deduct 2 from the 16 and it became 14. So in this case we say it doesn't shatter the data set. So now we find through this analysis we found, okay, 2n is better than m in most of the cases. So let's see what are the properties of using a dichotomy set instead of the union bound. All right, so now also there's a recap for growth function. So we talked about when we have n number of points, we can define a growth function like m of h of n as the maximum number of dichotomy set. So in the case of 3 points that we just saw in the previous slide, so dichotomy set as 1 point could be 6. If the points are aligned this way, right? If you have these 3 points, if the middle one is minus and the rest are pluses, right? It's tough to use one perceptron to distinguish these two. Just like the other way around, minus, pluses, minus. So it's going to deduct 2 from the 2 to the raise of n. That's why it becomes 6 in this case. In other cases of 3 points, like when they are like this, you can shatter the data set and it's going to be 2 to the raise of n. So in the upper bound, we thought, okay, m h of 3 could be up to 8, right? And we thought this is the maximum growth function for n equal to 3 data points, right? For the 4 data points I described in a previous slide, it was 14. And then we define a growth function as the maximum number of dichotomy set, right? So yeah, just like I mentioned, for n.3, we assume 8. For point, the growth, we assume 14. So now using these values, we also define VC dimension in the previous lecture. Another point to consider is growth function is actually the effective number of hypotheses of h on the training point. So now we're interested in gauging our complexity depending on the training point. So if you have 3 points, what's going to be the maximum number of hypotheses needed? Or could be had, right? All right. So let's recap also VC dimension. That was the first two letters were the name of the authors, and this is dimension. So Vapnik, and Chernonen, Kiss, I guess. So yeah, they defined in 1971 a VC dimension based on this value, and they defined let k be an integer such that the maximum growth function for k point is smaller than 2 to the raise of k, then k could be a breaking point, right? Because after that, this value will be bigger. Before that, it's going to be smaller. Okay. And just for the recap of VC dimension, let n be an integer such that this value is exactly equal. So instead of this, this is equal to all the binary values, the combination of the binary values, which are 2 to the raise of n. And if you add 1 to the data point, we have this condition. So the growth function for the one more data point is going to be smaller than 2 to the raise of n plus 1. Then we can say the VC dimension of our space given our data points is n. And we call this d of VC here. So this is good. At least we have a better upper bound for the complexity of the model. On the other side, having a breakpoint value such that above, so this is a very important note to consider. So the existence of a breakpoint puts a severe restriction over the growth function. So although we can expand, although using the dichotomy, we can expand up to 2 to the raise of n as the upper bound, but if we put a breakpoint it's going to make the complexity of the space way smaller, because it's going to put a restriction on the growth function, right? So let's see what that means in the next slide. Okay, let's see an example of the restriction of breakpoint over VC dimension. So say we give only the growth function of 2, maximum 3, right? What does this mean? For each of the 2 points in our space, say for each x1 and x2, we allow them to have 3 different dichotomy set, right? So given this restriction, so this is our restriction. Breakpoint restriction. So given this restriction, find the maximum value of the growth function for 3 points now. So if each of the 2 points cannot expand more than 3, what's going to be the growth function for 3 points? Right? And we see that by simply having that restriction, it's gonna downsample the number of times we can expand to a high number. So these are 3 points, x1, x2, and x3. This one is okay, all pluses. 2 plus, 1 minus, still okay. If you consider each of these two, let's talk about these two. x1 and x2 on both cases were pluses. So they were only having one value to play with. So these two are okay. How about x2 and x3? So plus, 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 minus. So they have 2. Still they're okay because the upper one was 3. How about x1 and x3? So plus, 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 minus. Still okay. Let's talk about the third row. Still okay, because if you talk about x1 and x2, if you compare them, you're going to have one value and 2 values. Okay. x1, x3. 1 value, 2 value, this is the same, still okay. x2 and x3, still okay. They have now 3 values differences. Plus, plus, 1, plus, minus 2, minus, minus 3. So now, if we have the other line here, minus, minus, plus, this would be the result of the restriction, and we can't have it in the dichotomy set. Whereas if we didn't have this, we could have had, right? Because this one becomes the third, more than the third one, that we have each of the 2 points are having more than 3 combinations, right? Here in this case, we're going to surpass the third combination between x2 and x3. This one is still okay. So now you see that instead of 2 to the raise of n, now we only have 4. And that was because of the restriction of the breakpoint. So you see that putting a breakpoint can severely downsample the size of the dichotomy set. So it appears that when 2 points, the restriction on 2 points are 3, the number of dichotomy set cannot be more than 4, right? And we observed it here. All right. So, having all these, we define also the VC inequality. So, assuming the VC dimension is any number below infinite number, so we have this inequality. So, the maximum growth function would be smaller than the summation of all the combinations of k of n, and then this itself is going to be smaller than n to the raise of the VC dimension of h plus 1, right? And this is called VC inequality. And it generates a polynomial complexity for our machine learning models. At least we have a polynomial bound using a VC dimension. And if you increase that, it's going to increase polynomially, right? P.
Another inequality is that n choose k, the common for.
Yeah, that's right, that's right. And this one is here. So this value plus 1. Okay, let me just close this again. Okay. And also we define the probability of delta G, which is the differences between your in-sample and out-of-sample error. The differences are within epsilon, and this probability is always smaller than equal to k1 growth function, k2 exponential raised to k2, and epsilon 2. And then we mentioned that these two hyperparameters, k1 and k2, are defined as 4 and 1/8. So we basically arrive up to this point in the previous lecture. Now, using this inequality, now we can define confidence levels again, those deltas, and using deltas we can define epsilon as well because of that. So now we have more freedom to play around with those parameters that union bound and Huffington's inequality we're trying to set as an upper bound, right? Now we understand that we have an inequality that increases polynomially in n. So this is good at least. All right. So in the previous example, that VC inequality, say you have n as 3 and VC dimension was 1, right? So we can say using this inequality that the growth function using these 3 points is always smaller than or equal to the combinatorial, so the selection of 0 and 3, 1 and 3, which is equal to 4. And we saw that already in our example, right? When we had x1, x2, and x3, and we expanded those values, these were 4, right? As we observed. Okay. So you see that it's almost similar to the union bound with some subtle differences. Okay. So, just like before, we could define delta equal to the value of k1, growth function, exponential minus exponential k2, and epsilon 2. So with the probability of the confidence levels, like this, these two. So say the confidence level was 95%. So this was 5%, and this becomes. So we say with 95% confidence level, we say that this inequality holds, right? The test error is smaller than or equal to training error plus an epsilon. So they are within each other with epsilon. You can just define epsilon from this, and then it's going to be the root square of delta divided by n, the log of 4 mh of 2n divided by delta, which is equal to my PowerPoint today. Eight over n log of this value 4 2n VC dimension plus 1 divided by delta. And we call this omega with these hyperparameters: hypothesis h, number of data points, and delta, right? So it's a function. It's a function such as theta over this that uses the VC dimension and the number of samples to define the complexity of a model. So now we have a better understanding of how we're going to define the complexity of the model using the VC dimension, the number of hypotheses needed, and number of data points, and delta, right? The confidence levels. So if we increase n, we can have the behavior of increasing the complexity of a training model or test model. And I'll show you an example in the next slide. Okay, let's go back to the good old figure that we talked about many times. So now we understand that VC dimension actually help us to define how we're going to overfit or underfit a model. So the optimal value for this VC dimension, we call it here VC dimension star. So it stands somewhere around here. So the red line is the out of sample error, green line is in sample, and this is omega, which is the complexity, increasing of complexity of the model, which is, you see that it's going to increase polynomially. I just see the curve here. So remember the first session I was talking about underfitting and overfitting. So now actually we can have a value to quantify that. So if the VC dimension was way bigger than the optimal value, we are overfitting. On the other side, if it was smaller than this, we say that we underfit, right? And a rule of thumb in many machine learning practices, normally they use the data point as 10 times VC dimension. So if your VC dimension was like 3, if, for instance, if they have 30 points, that would be sort of in the middle of, having an overfitted or underfitted model, which is a good point. All right, now let's see an example for linear classification. How we're going to use VC dimension for linear classification. So remember when we have the hypothesis h of w as a sine of wtx, which was our perceptron, it accepts the x's from r d plus 1 dimension and then map it to either plus 1 or minus 1, right? And all the w's are also in the R space. So VC dimension tells us it's going to be d plus 1, or the number of parameters of w, right? Let's see if that holds. So in order to do that, we have to consider two cases. So part 1 and the part 2. In case 1, if n is smaller than d plus 1, or in case 2, if n was d plus 2, right? So on part 1, if n is smaller than d plus 1, then there exist n points, given this assumption, there exist n points that are shattered by h, right? That was the definition of the hypothesis shattering point that I described in the second slide. On the second part, on the second case, if n is equal to d plus 2, thus we can say that was a breaking point for h. So now let's see how we're going to provide a proof for each of these two cases. All right, so number 1, let n is d plus 1, right? So we have d plus 1 points that are shattered by hypothesis h. So starting from d equal to 0, so these are d plus 1, you have x0 as 1 and n times d, 1 and d times 0, and also 1, 1 up to the end of the vector, which is d, and also the last line for xd is 1, 0, 0, 0, 0 up to 1. So each of the y values are like y 1 and 0, or other variables, we call it here e1 up to ed, right? So these are our points in a binary classification, and we have d plus 1 of those, starting from 0 to d, right? So in order to provide a proof for number 1, given any y from y0 up to yd, which are here, we show that there exists a vector such that this value holds. Perceptron actually, so this is the value of the perceptron. The sine of wtxi is equal to the sine of xi transpose w. So you change it, and that itself is going to be equal to xi t of w. So showing this, we show that the condition number 1 holds for n equal to d plus 1. So So in order to show this, you just have to expand their matrices, right? So the matrices of d+1 points and also the w's. Okay, so for each of the equations, we're actually doing one linear constraint on W. Thus, we have d+1 equations and d+1 unknowns. Right, this is unknown. So we can write the vector format. So y has the vector value of y0 up to yd, d+1 value, and it is equal to x, t, w, right? And w itself was the data points, d+1, and this matrix should be invertible. So you have to multiply it to the w. Okay. So given our data points and the dichotomy set that they provide, because they are 0 and 1, right? We can see that the determinant of this matrix is 1. W. Sometimes they call these matrices with determinant equal to 1 unimodular. So okay. So we can see that for d+1, this holds, thus the proof is sufficient. So how about d+2 points on a second case? Will this argument work on the d+2 points? Now we're going to see on the proof number 2 for the second case in the next slide. All right. So let's see for d+2 points. Now n is d+2, and our x's are d plus 1 in R space. And we see that these points can't be shattered by edge for d plus 2 because these values, the x1, x0, x1 up to xt, are linearly dependent. So there's no way, just like the example that I provided in a first of the lecture when we had 3 x's and we had a restriction over m of h equal to 3. So for each of the 2 points, we couldn't expand more than 3 different combinations, right? And that's why we saw that instead of 8, we couldn't expand more than 4. So it put a restriction on the points because these two were in a form, they were linearly dependent. So in this case, when we had 0, 0, 0, suppose just x1 and x2, you had 1, 0, 0 and 1, 1, 1 wouldn't hold because it would expand the upper bound of the restriction of 3. So we couldn't have 2 to the raise of n in this case, and it would be only 4. Just like this, for n equal to d plus 2 points, since all these values, all these data points here are going to be from 0, 1, and then 1, 1, 0, right? They are linearly dependent, so there's no way that these points can be shattered by edge. So now let's assume a linear combination of these a1 x1, a2 x2, up to ad plus 1 xd edge, right? Where these components, a1 is not 0, because if they are 0, they're going to make this go away. And also x0 is not 0, right? For some I, we can claim that the following choice can't be achieved by any w's within the R space of d plus 1. Okay. Let's consider one of the cases. Suppose your true label was, suppose your y0 was minus 1, and you were considering plus 1 and minus 1, right? So for ai smaller than 0, it would be minus 1. For ai bigger than 0, it was plus 1, right? So let's say contradiction. So for contradiction, we suppose we have a w that satisfies this perceptron, right? Now, we have to just claim that this was plus 1 so that it contradicts the minus 1 here, right? The hypothesis was predicting plus 1, but the real value was minus 1. In this case, we can contradict the proof. So we have two cases. A1 bigger than 0, the first case, and A1 smaller than 0. For the first case where A1 was bigger than 0, yi had to be plus 1. Thus, this calculation, the multiplication of w and x's would be pluses, right? On the other case, this would be minus. However, if you compute ai w g x I, it would be plus for all the i's, right? You see that on both cases, the value a1 multiply wt multiply xi are positive, right? Here. For all the i's from 1 up to d plus 1. Thus, we can see if you expand this matrix, so wt multiplied by the x, so these are the linear combination a1, x1, a2, x2 up to ad, xd. These values are also plus because a wt x was plus. And the output of the perceptron was plus. So that would be for the first order. If you consider the second order model, when you have quadratic form, and if you calculate that, so the VC dimension of the second order becomes 6, and you see that we increase the VC dimension by increasing the complexity of the model, right? And just like that graph that I showed you, your omega would increase polynomially in a polynomial order by your VC dimension, right? This is your complexity and this is going to be your error. So that was just an example for using VC dimension for linear models in first and second order. And you see that increasing the number of n or increasing the complexity of the model increases polynomial order using your VC dimension. So I'm just going to stop here and then carry on the biases and variances on Friday. Any questions? Okay. Have a good day, guys.